Again, apologies for the delay and welcome. I am Rathana Peou from the University of Brussels. I'm the academic co-director of the Brussels Institute for Advanced Studies and I'm the coordinator of the sub-team Food Systems and Renewable Policies in and beyond Europe. And after two wonderful lectures on this really timely topic of forest strategy and renewal in Europe, Professor Matthews and
our horizons a bit and looking at food systems beyond Europe in Southeast Asia specifically. BrIAS fellow Dr. Rathana Peou Norbert Munns. Hello Rathana, welcome. Will be joining us digitally from Thailand today, if I'm correct?
Correct.
And for the seventh BrIAS talk, and she will talk about the development of climate resilient agricultural policies in Southeast Asia. She is affiliated at the Copernicus Institute of Sustainable Development at Utrecht University and the Regional Office for Asia and the Pacific of the United Nations Food and Agriculture Organization. Dr. Peou Norbert Munns uniquely combines an academic expertise with really hands-on experience with the practice of foresight planning in food systems within the context of climate change and the challenges that brings to food security. I won't read her full CV, although it makes a good read because she has done so many interesting things. But she has worked as a researcher at the Environmental Change Institute at Oxford University. She was the deputy director of the Center for Sustainable Development in Bangladesh. She has been an international consultant for many agencies such as the USAID, ECHO and EU, and she has worked as a humanitarian worker in Sudan, Pakistan and Bangladesh. Needless to say, I am very honored and really delighted today to introduce her as our next speaker, Dr. Rathana Peou Norbert Munns. You have the digital floor.
Thank you very much, Professor Nell, and thank you for your kind introductions. So, bonjour, good afternoon, and good evening to all. Just checking that the mic is okay and that you can hear me clearly. Yeah.
We are not hearing you.
Okay, that's interesting. Yes, we are. Okay. Good. All right. So just to be sure then. So bonjour, good afternoon and good evening to all. Thank you very much, Professor Nell, for this very kind introduction. When last year you contacted me, I was very surprised and I think I have to say very deeply humbled to be invited to join the BrIAS First Fellowship. Not only the team is something that is really at heart for me, but I was really looking forward to work with colleagues and fellow under that team. So I'm really pleased to be part of this digital platform and unfortunately cannot be with you in person. Allow me then to share my screen if that's okay with everyone. Just checking that everyone can see the screen.
Yes, we're seeing it.
Perfect. So my today talk is about developing climate resilience agriculture policy in the ASEAN member state, what we call the AMS, framing today the future food system. This has been my focus of the work that I have been conducted in Southeast Asia for about 10 years now. First starting with CCARS, which is the Climate Change Agriculture Food Security Research Program of the CHR, and now recently since last year with the UN-FAO Regional Office of Asia and Pacific. Although there is not yet an equivalent of the Green Deal policy at the ASEAN level, there are many legislative work that could provide perspective and feed into the debate surrounding sustainable food system. As of today, there are 50 parties that submitted their long-term strategy for carbon neutrality. At the ASEAN level, the most recent submission was from Cambodia last year in December, joining then Singapore, Thailand and Indonesia. I would like to highlight, even before starting to dig into the subject, that the EU and the ASEAN have a very long relationship of a bit more than 40 years. Back in the time, ASEAN the EU was the first ASEAN formal partner and formal dialogue path of the ASEAN. Right.
Okay.
Oops, sorry.
She still talk?
Yes, sorry. So here a little bit more about EU and ASEAN, and I think it's very important to really start to understand a little bit more both of the context. One of the key highlights here that I would like to again emphasize is that the EU is the ASEAN third largest trading partner, while the ASEAN is the EU fifth largest partner. So let's talk together this little flight, or long flight if you consider that, of only 9 hours from Brussels, or 7,000 kilometers of walk for the next 30 minutes. And then we will have those question and answer. In terms of expecting learning and reflections, I have already categorized 6 kind of areas which I hope are going to spark discussion in the future. Exploring key characteristics of the IMS food system, which is the ASEAN member states. Understanding key driver trends and uncertainties. Explore strategic policy questions related to agriculture and land use planning. Introducing as well key policy formulations tool for resilient agriculture and food system. Learning from case use, and as Professor Neil was highlighting, a lot of my work is in the practice of formulating better policy, more robust policy, and I hope that I will have the time to introduce you to some of the work that we have been conducting in Southeast Asia, and as well exploring remaining gap and challenges, because currently, there is no perfect response, there is no perfect solutions. It still be a major learning curve, and it is very important to really identify those gaps and challenges and identify how we can overcome them when we are talking about sustainable food system, climate resilience food system, and how policy can actually impulse that transformation. The outline of the presentations of today, of the talk of today, is pretty simple. Setting the context, policy formulations, and then remaining gap. In terms of setting the context, a couple of figures here. I think it's very important to always emphasize on the big fact. The total population of the IMS was of last year of 655 million inhabitants, compared to for the EU of 448 million. ASEAN is one of the world's fastest growing economical region. And if ASEAN were one economy, it will represent the 5th largest in the world. In terms of agriculture, the GDP or the regional GDP of the ASEAN reached 10.2% of the GDP. The largest share of agriculture product in the total export is from Myanmar and Laos, with 24% and 23%. Another key highlight when we're thinking about setting the context of the IMS is that when we think about the Southeast Asia, we think about the vulnerability of this region. But not only is that region vulnerable to climate change and to natural disaster, it is as well, and I really want to emphasize on that, it is as well one of the most rapidly increasing region emitter of greenhouse gases. So coming back to the vulnerability, 4 out of the 10 ASEAN member states are among the top 10 countries most affected by extreme weather. Over the last 10 years, the number of natural disasters that affected population in the IMS have doubled compared to what it was in the early 2000s. And meanwhile, if you take out of those 10 countries, just 5 of them, Thailand, Vietnam, Indonesia, Malaysia, and the Philippines, you will get 90% of the total greenhouse emission of Southeast Asia. This is a very important part when we talk about climate change and we talk about resilience. The focus cannot be only on adaptations, but need to look at as well low emission pathway and how we can build those low carbon emissions agriculture system in the future. I guess many of you to a certain extent have been following the COP26 in Glasgow, and many of you must have here very inspiring speech and call for climate urgency. Yes, climate change is the greatest risk facing us all. Currently, even the IPCC is stating that global warming is expected to reach that dangerous 1.5 degree as early as 2030. Same report of the IPCC states that Southeast Asia will continue to be one of the planet's most vulnerable regions to climate change. And under the most negative scenario, which is called the business as usual scenario, or for those that are a bit more familiar with the RCP 8.5, climate change will cost Asia more than a quarter of its GDP by 2050. So let's step back a little bit and let's emphasize again on agriculture and the importance of agriculture. The UNFAO have been quoted a couple of times with their different projections. And to meet global food demand by 2050, agriculture production must increase by 60%. And I really want us to really think, how could we achieve that increase while trying to be sustainable, trying to be resource efficient, and building on or developing further on low emissions or decarbonization pathway of the agriculture sector. In Asia, and again, I'm looking at the AMS, so the ASEAN member states. If you look at just two sectors, which is the agriculture and the forestry, the total land use of just two of those sectors is of 79%, is about 79% of the total land area. So when we think about shifting agriculture, when we think about intensifying agriculture, moving to new crop, we're talking about 79% of the land that we have in the AMS. Rapid population growth and climate volatility in Southeast Asia will push demands for food in the region by 40% by 2050. Major crops are at risk, with projections that are highlighting a significant decrease of suitability and yield for major crops. Those major crops, rice, coffee, cacao, maize, cassava. I mean, I can continue, and the list is rather quite long. So when we're looking not only to the different crop or the different agriculture practice, one of the key features as well in the IMS is the workforces that is dedicated to that sector, to agriculture. And I think people really need to realize that that sector employed an average of a third of the total workforces in the region. And on the top of the list, if you look at Laos, 61% of the population is working under agriculture. Vietnam, 37%, Cambodia, 34%. One of the key features as well that mark this agriculture sector in the AMS is this move or these transitions to not anymore a substantive agriculture, but a more commercial. However, the rate of adaptations of technology and innovations or climate smart agriculture is still limited. For those of you that don't really capture the impact of climate change on agriculture, allow me just to emphasize again, not only the highest temperature are going to reduce the yield, the heavy rain as well, warmer water that are going to likely affect the habitat and food of many fishes. The elevated CO2 and increased salinity in soil can be detrimental to the plant and the ecosystem alike. I think this is really important. We're talking about a region that is a key green basket. And we're talking about impact of climate change that will be one of the most severe and the most costly in the world. So when today we're talking about climate resilience and we're talking about climate resilience agriculture, yes, it matters. Yes, it is very important. And what can we do and how we can support it is equally important. Just to come a little bit about the food system within the IMS, so ASEAN member states, key trends that we'll talk globally and we'll talk as well for the EU: population growth, changing diets, climate change, conflict, natural disaster, the COVID-19 global pandemic, rapid urbanizations and middle class growth. I think all of those key drivers of trends that we see globally and regionally are extremely important to look at the food system for what it is. The food system is an extremely complex and interlinked system. So when here in the ASEAN, policymakers at national or regional level are addressing agriculture. They are addressing agriculture in all different angles. They are addressing agriculture within the complexity as well of the food system, its uncertainty and its vulnerability. Again, agriculture is a critical livelihood for smallholder farmers, both driver of economical growth, but as well of poverty alleviation. No need to say as well of food security. Reports indicate that the loss could be in Southeast Asia of $28 trillion in the next 30 years. And I like to remind anyone that any shock or change that we will have in agriculture or in the food system in the ASEAN member state will not only be felt in this region, but with no doubt its partner region too. So let's dig into the talk of today and really looking at policy formulations and tools. Policy are not happening in a vacuum, and I'm going to emphasize on different frameworks that are very important to remind to all. Key questions here is what are available tools and data that support robust decision-making and long-term planning? When we are looking at agriculture, and again, depending about what type of land zoning we are going to promote, what type of crop we're going to promote, what type of agroforestry we're going to promote, you can't be in a short term. We are looking at change of land, change of soil, change of area that are extremely significant. And this is why it is very important today to really discuss about how we think the future and how those agriculture policy are midterm and long-term. So you should now, and it's really legitimate from your side to ask, what is climate resilience agriculture policy? Well, there's no perfect definitions, and I think there's many different type of definitions, there's many different type of practice, but in general, climate resilience refer to that ability to prepare for, recover from, and adapt to climate change impact. I think it's very important to emphasize on those three dimensions: prepare, recover, and adapt. I like to use then for a definition of climate resilience agriculture policy, a definition that was developed in Philippines by the Climate Resilience Agriculture Department. And the definition is reflect an ambition to improve the integration of agriculture development and climate responsiveness. It aimed to achieve food security and broader development goals under a changing climate and increasing food demand. So what is climate resilience agriculture policy? It can be many different aspects of the food system and of agriculture. But the uniqueness of addressing climate resilience is the uniqueness of addressing the comprehensiveness of that system. The Global Climate Actions and the Marrakesh Partnership have defined key area of policy under the climate resilience agriculture: climate risk, early warning, preparedness, climate risk governance, nature-based solutions, climate proofing, risk transfer, sharing of knowledge, volume, quality and access of public and private finance. Those are key policy areas under climate resilience agriculture. As I said before, nothing is happening in a vacuum. The push of climate smart agriculture, the push of climate resilience agriculture policy is coming at multiple levels. Let's look back a little bit with the international framework. Many of you are fully aware, and I'm not going to emphasize too much with the UNFCCC or the IPCC, but just one very important thing, not only from the COP26 in Glasgow, but back in with the Paris Agreements. Climate ambitions and decarbonization pathway of the food system have been legitimized with a real commitment at the global level to keep global warming under 2 degrees. So those climate policy and those discussions we're going to have in the next slide are legitimate by that international framework. And in the IMS, the Paris Agreement, for example, have been a real push of not only thinking and talk, but actual policy. Recent research showed that just in a period of 10 years, 64 climate policy orientated on agriculture have been signed by the different countries. And I think this is a very important push that we need to recognize. Another international framework, which is the SDG, tackle as well the different issues that climate resilience policy in agriculture are trying to address. The SDG 1, 2, 8, 9, 12, 13, 15, and 17. So there is really an international framework allowing that blossom of legislation. At the ASEAN level, and I think this is quite important for some of you that are not really familiar with the ASEAN policy framework. Much more before the Paris agreements and even in the early 2000s, the ASEAN identified climate change as one of the key risks that will impact the region. And from 2000, numerous legislations, numerous guidelines, numerous joint positions have been published within the ASEAN. And I think this is extremely important to put again on this talk. At the regional level, this policy framework is extremely rich, extremely long in terms of history. I don't know how many of you know that, but the first time that the term resilience and climate resilience is appearing in the ASEAN policy is back in 1976. This is quite important acknowledgement of that threat, but as well of the need for governments and this region to address that threat. So couple of quotations that I put: climate change threatens the agricultural production and indirectly food security, ecological stability and sustainable development of the ASEAN member state. This is something that is really inherent part of the ASEAN culture and the ASEAN legislation. To address climate change and its adverse impact on socio-economic development and health, the environment through the promotion of appropriate agriculture practice, climate smart agriculture practice, building competency. There is a really big discourse and actions related to building capacity and skill, providing access to financial resources, and enhancing regional and international collaboration. And it's kind of, you know, with no surprise that within the ASEAN, what we see over the last 20 years, 30 years, but here with the ASEAN Climate Resilience Network is, I think 7 years ago, is more network, more think tanks, more civil society really engaging in that climate resilience in terms of what type of legislation need to be put in place, in terms of access to finance in order to promote climate resilience for smallholder farmers, but as well in terms of what kind of climate smart agriculture practice can be promoted. And this is again a very important step where those legislations, those kind of legal framework are not just talk, they are actually really targeting different practice, trying to promote climate resilience for different type of crop, different type of subsector inside agriculture. And the forestry, it will be agro-industry, fishery as well. Sorry. So the question now is looking back at different policies that have been developed. And again, I'm not saying they are perfect. It is a learning curve and a lot needs to still be improved. But what can we learn about how to develop, how to formulate, and how to test those climate resilient policy? As Professor Neil said before, I'm a foresight expert. I don't know how many of you are familiar with foresight. So allow me just to come very quickly to key definition. So foresight is a label for method that aim to explore what the future might bring, such as scenario. And scenario are a way to address uncertainty about future by creating coherent, internally consistent storyline that explore plausible future state. In my work, I work with a lot of modeling. I work with a lot of teams that are focusing on forecast. Foresight, by definition, is long-term. It's another time scale. And one of our tools, which is the scenario development, go beyond prediction. It go beyond one future. And when I say go beyond one future, it's because it has been a trap for a very long time to think that the future we want, the future we desire, will be the only place where your policy will be written and narrated. In the work we are conducted with CCAFs and before, and now with FAO Regional Office, we are looking at plausible future. We are looking at future that can be all true. And why is that important, and what makes that something different, something better? Well, because when you write that policy, when you are looking at adaptations or mitigation actions under the agriculture sector, looking at only one ghost scenario will not allow you to test those actions or those recommendations outside a pathway or outside a scenario that is not the one that you want. And as of today, with the uncertainty, the risk, the change, what policymakers want to ensure is that the policy they are writing today, the agriculture pathway that they are writing as today for the future, are policy and actions that are going to have an impact. That impact pair with what we call the low regret option is an engagement that we see more and more from different sectors in the regions to really think about the future and this climate resilient future. So for those of you that might be kind of interested about how we develop socioeconomic scenario, how that kind of more qualitative approach allow us to explore that possible future, those are kind of steps that we have in general doing that exercise, which is about engaging and influence mapping, qualifying driver of change, developing scenario, quantifying the scenario analysis, and the policy process and recommendation. The first step is quite, let's say, it's one of the most interesting for me. It's you will define the scope of your work in agriculture, and for example, one of the departments under the Minister of Agriculture of one country will ask you to really look a little bit more about coffee. So you will start with mapping the different stakeholders and their influence, not as of today, but as well as of tomorrow. And at that moment, with that kind of engagement with the people that are going to participate to your scenario workshop, you are going to be able to transform their interaction with today and project them with multiple future. And I think this is a really not only interesting, but it is a very significant step for many policymakers. Another part of my work, and again, scenario is just one part of the foresight planning that can be done and the type of support that can be done with the climate resilience agriculture policy. What we could do as well, and what it's being done in the IMS, and here's an example for the work that we are doing in Laos, we're doing what we call the hotspot map. So different layer of AZ map, climate data, looking at the difference between the suitability of a crop. In this one, we are looking at cassava. And what you see on the right of it is the difference between the current suitability and the future projected one under the RCP 8.5. If you remember, this is the business as usual, so the worst case scenario. So what you see on the right, and I'm sorry, it's kind of rather small, is all of those red dots. So usually when you see red, it's like, it's an alarm, right? So when we produce that kind and we communicate that hotspot map of the future of the agriculture under one specific crop, which is the cassava, we initiating a dialogue with the policymaker, both at national and at provincial level, for them to understand that in the next 30 years, some of the provinces that are currently producing cassava are not going to be any more suitable to produce cassava. This is a major learning and a major insight for them. Now they have a couple of options. It's not because in the future it's not suitable that they have to shift the crop, but it's a great call to say that there are a major need to push for irrigation, push for new kind of climate finance, introduce new type of climate smart agriculture practice if we want to continue to have cassava in those regions. But for some policymakers, again, at national or provincial level, some of them will say, okay, well, if cassava is not anymore an area for us to invest, what should we do? What other crop are more suitable what can allow me at the provincial level to ensure that we maximize the resources against those different climate scenario and socio-economic scenario that have been presented. And I think this is very important part of that kind of policy outcome that those foresight planning approach and scenario developments are offering. Because it's allow you to allocate those areas that will be the most suitable for the crop production. Again, I remind to everyone that when we talk about the EMS, 78% of the land is used by agriculture and forestry. And when we talk again about the ASEAN member states, we have, in terms of deforestation rates, one of the highest one. This deforestation rate is to feed new type of agriculture land. So if we're changing the whole pattern and the whole land use of those countries and those regions, policymakers of today need to be sure, again, low risk options or no regret option, they need to be sure that the crop or the agriculture system that they are going to promote for their own food security or the livelihood of their people or for the export are something that is suitable for the different futures. Another type of work that we are doing, and again, I think this is really kind of important because it is the interface. When we talk about climate resilience policy on agriculture, we're talking about major phenomena of data. We have more and more data, we have more and more climate science, we have explore more and more climate smart agriculture practice. So how can we digest those different data, harmonize those data, and be able to project different pathway or priority recommendations that policymakers can take to a new level, and with those policy actions attract or enable a better future. So what you see on the right is what we call a story map, and that's we're doing that work as well in Laos. We have been doing that in different regions where we are exploring the futures of banana. Again, we start in the same way. We have AEZ mapping, we have different type of climate data. We're looking suitability of that crop. And then we have different discussions in terms of priority actions, in terms of different scenarios that have been developed and how those priority actions are actually robust or not. And then finally, we have those recommendations. And one of the key recommendations are then taken back to the cabinet of the Prime Minister and being discussed. It's not just discussion for discussion. The Minister of Agriculture have then in his hands way to leverage a new budget, a new national budget, or could go to a partner and find new way to unlock or at least some climate finance. So when we talk about climate resilience agriculture policy, we are as well linking to that very essential part of a decision maker, which is how do you ensure that action is going to be put in place? How do you ensure that you can unlock that investment or that budget? So I'm just going to, for the last 5 minutes of the call and before taking the different questions or the comments from the team, let's look at a little bit more the different gaps and the challenges. I hope that now you understand a bit more about the context of the ASEAN member states. You understand a little bit more about the complexity of the food system, the need of climate resilience agriculture policy, need that are justified and legitimized by multiple international and regional framework, and the need at local level to address the climate dimension now. So a couple of gaps and challenges. So when we are navigating that complexity and uncertainty, and I think this is very important, more and more policy are expecting to be more and more that kind of inform-based policy. So there is a crucial link or interface with science and with data. Now, what type of data? What are the level of the data that are available in climate, in socio-economic dimensions? It varies from one country to the other one. Singapore is totally different from the data governance and the data maturity of Cambodia, for example. So how can we work with those data and those information in order to ensure that people that are in a position to take decision today for the futures are in the best position? This requires a lot of work in terms of credibility of the data, in terms of building the data set, and it takes years and years. In some of the case, a data set just for agriculture for one crop could take up to 6 months to 1 year. Do we have that time? That's another question. The data analytic, it's not because you have data, it's not because you have the climate science that you know how to read it and you know how to prioritize. There still be a lot of need in terms of capacity building related to data analytic. A fourth gap or challenges is unlocking finance and budget. I talked earlier, and it was easier with Laos about the national budget because there is a national budget. But when we are looking at the intensity, the frequency of natural disaster, the very high level of impact, again, I remind you that about 25% of the total GDP will be lost from now to 2050 in Southeast Asia. Unlocking finance and budget is key if we want to be able to address those issues and if we want the agriculture sector to be resilient enough. Now, with the speed of change, the access to technology and innovations are key. The ASEAN member states are still suffering from different aspects, and all of you will think directly about food security, poverty, but there is as well this energy poverty. So many of that access to technology and innovations are actually rather limited in the country that need it the most. And finally, I like to just really emphasize that when we are supporting, developing or testing those climate resilience policy on agriculture, the need is not only to focus on what needs to be mitigated or how to reduce the costs, the loss or the damage, but as well to be sure that those governments and the agriculture sector can seize new opportunity, new area that can grow those crops, new innovation that can reduce the impact of climate risk on the yield, for example, for rice or for maize. I think this is very important to look at both the opportunity and the negative impact of climate change. And agriculture is really in that unique interface for doing that. So thank you. I hope that I limited my time well for having the questions and the comments from Vincent. Thank you.
Thank you, Rathana. Thank you so much for this extremely interesting lecture. I was wondering if any of you had any questions. And I will give a digital applause as well. Thank you again. Yes, please raise your hand if you have any questions. Yeah. Yeah, go ahead.
May I ask a question? Yes. Well, do you hear me all? Do you hear me? Well, okay. We saw that slide a couple of slides ago. We saw all the ministers of agriculture hand in hand showing agreement. But I can imagine that there are also conflicting interests because, well, you have several conflicting interests. On the one hand, you have food production for the local population, but on the other hand, you also have agricultural production for non-food exports, for example, various kinds of oils. So I can imagine that there's a conflict between the need to sustain people, but also to raise money for by export. So to what extent is your job made more difficult by the conflicting interests within countries, between countries?
So thank you so much, and it's a very interesting questions, looking really about the competing priorities and different agenda of different type of people that are inside the food system, from the people that produce to the people that are going to sell, to those that are going to try to get money and going to emphasize not on the food security or the national priority, but thinking about exports and increase of the GDP. It is like one of the most essential parts that we have. I will say that in the ASEAN member states, one of the key fundamental part of any of the constitution is food security. And it will be very, very difficult to have country moving away from rice, from cassava, from maize, from those that have been a part of their culture. When COVID-19 starts to hit the region, all of the country decided to keep what they were producing in terms of food inside the country. And I felt that this was really amazing because the priority is the food security of the people. GDP and all is not as much something that they are looking at. And there is really a lot of culture behind, and I think there is this enthusiasm that we have when we are talking about different ASEAN member states, but all of them have this very unique attention to food security and this unique attention to increase the food opportunity in the region by fighting against climate change. And this is really since more than 20 years.
Thank you very much.
Thank you. I see we have a question in the chat. I will just read it aloud. It's from Christopher Vincent. I have a few questions. What policies have led to reduction in food insecurity in the region? What has the impact been? How has the efficacy of resilient strategies been verified? So
in terms of policy that have been reducing food insecurity, there are multiple policy, both at regional and national level. A lot of as well of the ASEAN member states country benefits from a lot of money coming from donors as well in order to increase that food security. A lot of work has been done as well under the SDG 1 of zero hunger. So yes, there's multiple aspects here, but a lot have been done. A lot still need to be done. I'm not saying that everything is perfect, but there is actions and there is money related to that. Then I didn't hear the second part, I think, of the question.
What has the impact been? And how has the efficiency of resilient strategies been verified?
So in terms of the efficiency of it, there are multiple guidelines that are looking at climate smart agriculture and the impact. A lot of those practices are being evaluated regularly, because the idea now is to be able to scale up those practice or those skill or those technique. One of the issue or the challenges is that many of those climate smart agriculture practice that are being promoted are very context specific. You know, it's specifically on one crop, it's specifically on one type of soil. So it is very difficult to scale up. But there are a lot of effort to really like monitor and evaluate. And that's why, you know, when I put at the end of my presentation, one of the gap really being data, still remaining data. This is still like a very identified gap by all of the stakeholders across the value chain of food system.
Okay, thank you. I am actually not in the room at the ULB, so I was wondering if there are any questions in the room, Christian? Are there
So I
any
will
questions?
ask, are there any question in the room? It was Christopher. Any other question here? Some more questions?
The challenges of a hybrid meeting.
No, they're all satisfied here. They have no further
No
questions.
questions? Okay. Are
One
there any
time,
more questions?
3 times. No regret. No.
No more questions from the public that is following the talk digital? Okay, then I will thank you again, Rathana. I'm so grateful. What time is it now in Thailand?
9:11 p.m.
Okay, thank you so much for working so late for us and for this really interesting and thought-provoking presentation. And now I'll give the floor to Christian, who will introduce our next speaker.
Thank you. Goodbye.
Thank you so much.
Thank you, Nell. Thank you for your presentation. So our next speaker is ready. So he did a presentation 2 weeks ago for this workshop. His name is Prof. Vincent. So in 2008, he gained a master in horticulture and fruit production from the University of Arkansas. In 2016, from the University of Florida, he worked on papaya and water stress, I guess, in South Florida. Then he was appointed assistant professor in the same university. And Christopher works at the Citrus Research and Education Center. And that center is assisting the citrus growers, I guess, in identifying pest disease and implementing management. This is the case. So Christopher published around interference, sorry. So he published around 30 papers covering various aspects of plant biology. Christopher is interested into biotic and abiotic stress plant response. He's also focusing on photosynthesis, root hairs. Then Christopher teaches also advanced citrus culture to understand major challenges facing the citrus producers and to understand the citrus crop biological characteristics and overall the Floridian ecosystem. So my pleasure is to introduce you, and the floor is yours. So we're gonna share this. It works for you. Yes. Online is fine. Okay.
No.
Works.
No.
No. Screens. Why do we not this? Maybe he's waiting for the first one. No. And slideshow. I know. We lost the. Start. C'est quoi?
Just a reminder. In the browser. Browser. Yeah. So, okay. Click on the presentation.
But it doesn't show.
Click that down,
Yeah,
down there. Go back to Teams. Down.
But this is the bureau, it's not.
That's on you. Then you choose the
Click on.
Dalen.
And then click on this presentation. Full screen. Now.
But here it says it's sharing. What I can do, I will share the screen. I will put. Sorry. Now, yeah, I'm sharing.
Yours. Okay. Yeah, super slow.
Yeah, it's just a computer which is super slow.
You can see.
Yeah.
Yes. Okay. I will.
Okay. It doesn't even open it because for me it's because it's not copied in the computer. It's still in the USB.
If it's working from there, we can
Yeah.
up through there.
And it's actually open from this one.
Ah, okay, it opened from the
This
desktop.
one, yeah.
So go back to. I think we are not allowed to share. That's why.
Why?
Because we are not the
Not
session.
necessarily. She wasn't the other girl. She wasn't the one, right?
She gave.
So online it's fine.
Yeah. It's a full screen.
No, that's
So-
not that.
Oh, but then I can just go here. Yeah. I can just go through here and follow. Will that work?
The last one.
The Chrome tab.
Okay, let's redo. So, Christopher, Vincent, Lisa, Master.
He'll follow. Thanks very much. If you through that. So as you can see, the title of my talk is Evolution in Agronomy versus Disease, Globalization, and Climate Change. Piece the climate change part together a little bit through the presentation, but hopefully hopefully will be obvious. I think that there may be some then it'll be figured out. So I just want to give a little outline of what I'll be talking about. I'm going to talk about the evolutionary background of citrus, a brief understanding of citrus in Florida and the particular challenge that it faces, including environmental, physiological characteristics, and the most pressing challenge being a disease that we call Huang Being disease, and then how we can manipulate the environment around the trees to manage disease. And I'll go through a few specific examples of those that include particle films, shade netting, and intercropping, and I'll explain what those are when we get there. Can everybody hear? Can they hear me online? Is there anyone? Huh?
Online, okay.
Yep. Okay.
Yeah.
Okay. So the standard understanding of citrus in Florida is that citrus is a subtropical genus that is perfectly adapted to the warm, humid subtropics of Florida. Of course, I put a question mark in there, but first I want to mention that Florida is known as the Sunshine State. It's not an exaggeration. We experience lots and lots of sunlight in Florida. This is a typical early summer day. And so the two things that are emblematic of Florida, other than Disney World, are, yes, Christian's very excited about that, the Sunshine State and citrus. Those are what Florida is like about, right? However, I'm going to bring up a question of whether those two things really go so well together without some mitigation in a second. But first, I'll talk about evolution of citrus. It's a pretty diverse genus. It's actually a genus of tree species that are mostly crossable amongst each other. It's a very old genus. We know of identifiable, like morphologically identifiable citrus from at least 8 million years ago, and started off from one progenitor species, they assume, and I'll show kind of a little bit about what the current theories are about where it came from. The idea is that it came from what's currently the Himalayas, and that essentially the uplift of the Himalayas that occurred when the Indian subcontinent collided with Asia created a division of ecological zones to which the remaining plants essentially diversified, and then were eventually spread all the way down to Australia. So we have mandarins that sort of diversified in the direction of northeast China, pomelos that diversified in the region of the far southeastern Asia, and citrons that it's not diversified, but separated into the Indian subcontinent. And of course, human movement has really mixed this up a lot. So the things that we know as edible citrus fruit are mostly mixtures of those three main progenitor species, which are mandarins, pomelos, and citrons. And I don't want to get into all of the details of this, except just to show that, like, probably every citrus you've ever eaten, with the exception of maybe if you've been in Southeast Asia and eaten a real pomelo, or there might be a few pure mandarins that you might have been able to get. Everything else is a mixture of those different species to differing degrees of mixture, and they get really complex. The point isn't to go into the details of that complexity, but just to show that it's a highly admixed group at this point in terms of what we cultivate as citrus. Citrons are still used in traditional medicine, and calamandins are still used in traditional medicine. But now I want to get into a little bit of the kind of environment that those different progenitor species developed in, and there's some common attributes. This is a picture actually of mandarin in Yunnan province, which is not too far from the center of the assumed center of origin of citrus. But in terms of the specifics of where of the microenvironment in which these trees evolved, they all evolved as gap species. So they're from forested regions, and they don't exist as overstory, but as understory and gap environments. So partially shaded environments. So these are three examples. The example on the right is from Tachibana, so that's the most eastern species of citrus that's actually a derivative of mostly of mandarins. And so that's actually sort of partially wild cultivation in partial shade. And then here you have citrus growing in a relatively old forest in central China. And then here you have actually different subspecies of citrus on the Indian side, all growing in forested areas as either understory or gap species, so either partially or fully shaded by other trees. So, but then of course we take citrus and we grow it in a very different environment. But the main points are that it comes from South Central Asia, or South and Central Asia, and most of that diversification occurred in the humid subtropics, but in the specific context of as a forest gap species. And then it was moved by human traffic across Asia and to Europe, but then once European travel really exploded, it was moved directly from Asia to Florida by Europeans. Not the same varieties as were being grown in Europe at the time at first. So here's what sort of midway through the development of the citrus industry looked like in Florida. We have a lot of people picking. I'm sure they got all those people out just to take a picture, because usually it's not that many people involved. But I want to point out the kind of environment that we're growing in. This is originally a grassland. You can see in the back, somebody who's lived in Florida a little bit knows that those are citrus trees, which means that there's a swamp right there. So we're talking about a very humid environment, but we're growing on well-drained soils. And as you can see, we're just growing plants out in the field. We're not talking about a forested environment at all anymore. This is actually from Orange County, which is right next to where Disney World is now. So over time, a very vibrant industry develops, very diversified, lots of smallholder farms. They all have their own marketing strategy, marketing sort of different images of sort of exoticness from Florida to people from the north, ideas of health, nature, sexuality, exotic species, etc. And so that industry experienced a number of booms and busts depending on macroeconomics and depending on actually weather patterns with either freezes or hurricanes that sort of have caused geographic resituation. But overall, there was a general increasing trend from at least the mid-70s until about the year 2000, when a disease that's new to Florida was introduced. We call it HLB. That's because Americans aren't comfortable trying to pronounce words in Mandarin. It's short for formulate being, except it's not short for it because it takes the same amount of time to say HLB as formulate being. But we're comfortable with letters more than we are with trying to pronounce Mandarin. It was first detected in South Florida in 2005. And by 2009, it's detected well beyond the main citrus production region. So for those of you in the room, this big county in the middle, that's Polk County. That's where I live. And it's one of the largest citrus producing counties, but really the citrus production region extends from there down the center of the state till before you get to the Everglades. So it's this big south central region in the middle of the peninsula. And so most of those, actually, the disease had been detected by the end of 2007. So 2 years later, it's extended throughout all of the main citrus production regions. Initial strategies included things like removing diseased trees, but the disease transmission rate was too high, and that had to be abandoned relatively quickly. So I'll get into details about the disease in just a second, but over time, this is what happened with Florida citrus production. You see in the years 2004 and 2007, kind of a dip in production, and that's actually due to weather events. There were a series of hurricanes that actually damaged the yield on a temporary basis. But from that point on, from the time of the introduction of HLD, you see a significant decline in Florida citrus production. And so the overall United States production, the decline just reflects that citrus was the largest producer. Now it is not. You can see that gap between Florida and the United States is larger than the gap between 0 and Florida. That's because California has maintained relatively constant production during this time period, and Florida production has declined dramatically. It's an existential crisis for the Florida citrus industry. We've gone from 980,000 acres, so that's about 400,000 hectares, to about 350,000 acres, so about 120,000 hectares since in intervening time. So biologically, what happens? This is a nice picture of a healthy grove. My friend Maria is standing there for scale. This is an orange grove, a sweet orange grove. So this is what you want your citrus plants to look like, but this is what most citrus plants look like in Florida now. Obviously not very happy, and I'll get into some of the reasons why in just a second. So the disease is caused by a phloem-limited bacterium. It's persistent and it becomes systemic. So it moves throughout the entire plant. You cannot get rid of it as long as the plant is in the field. And it's transmitted by the agent citrusillid, Diaphora citri. And one of the reasons the disease extended so rapidly was that the vector was present and widely distributed before the arrival of the bacterium. So it was just sort of waiting to distribute the bacterium as efficiently as really could be done. What happens to the plant? Well, phloem function is disrupted, and that reduces root growth, that reduces fruit growth. You get a loss in canopy density. And then you have also something called pre-harvest fruit drop, which is that before the fruit reach horticultural maturity, they drop off. So you think you have, say 90 pounds of yield, and maybe you end up with only 60. And maybe before HLD, you expected 120. So pretty dramatic declines in yield and growth, and plants that are generally just sad to look at. So main point, HLD is bad, right? I'll get into more details in a second. And just since I'm talking about evolution, I just want to pose the question. So we know that this disease comes from South Central Asia, the same place where citrus in general comes from. We don't know the specific, point of origin, but we know it comes from places where citrus has been present for many thousands, if not millions of years. And so the question is, are these species co-evolved, right? I won't answer that question, but maybe you can. So enter my lab. We're the tree ecophysiology lab at the Citrus Research and Education Center. We have a bunch of people who work there, and we work with a lot of other labs. This list here includes biochemists, pathologists, and entomologists. And I just put all these people up here because everything that I show that's been done in my lab hasn't been done by me personally. Most of the time it's been done by one or several of these folks. Sometimes their pictures are up and sometimes they're not. So I just want to talk just a little bit. I know it's a little surprising to jump into water relations, but you'll see why I'm doing this in just a second. So citrus is adapted for the retention of water. So in monsoon type humid subtropics, you may have extended rainy seasons, but you also have extended dry season. And so species that are evergreen in those types of environments need to be able to retain water for extensive periods of time. So what citrus has done is evolve very water retentive leaf system. right? And so this is on the right, excuse me, left, yeah, your right hand side. This is stomatal conductance. So this is how open or how closed the stomata of citrus trees are over the course of the day. So this is just one characteristic curve, but you see this type of behavior. This is very unusual for tree species. Usually you see sort of a slow increase and then a slow decline over the course of the day, and then it kind of recovers in the late afternoon. The citrus is all over the place. And so I want to point out a couple of things. One is that when conductance is low, it's extremely low. It's almost zero. Basically, it's within the detection limit of our instruments. And then the amount of time that it's high during the day is quite small, but it's not contiguous. So it's about 4 hours of the day that account for the majority of the photosynthesis that occurs in the citrus plant. But it's not, 9 to 1. It's 9 to 10, and then 10:30 to 10:45, and then 12:45 to 1, kind of like that throughout the day. So you have this spike and drop. And this is just images of citrus cuticles, and I just want to point out this one characteristic, which is that not only does it have a thick waxy layer on the surface of the leaf, but it even has these little wings of wax that come up over the stomata. So when the stomata close, they're actually like doubly, it's like having 2 stomata closed there. So that's why that stomatal conductance is so low when it's low, is that those stomates are not just sort of closed, they're really, really closed. And very little water gets out through the cuticle. Okay, so I'm going to come back to this model a bunch of times. So what we see is that you can have really slow conductance out, and I won't get into the evidence behind it, but I just want to mention that the reason behind that is that it has really slow stem conductance. And actually that's the reason why you see those wild fluctuations, is that even though the leaves can restrict the flow of water, they often don't restrict the flow of water enough that the stems can move water in fast enough. So when conductance is high, the stems can't keep up, and that causes the leaf to begin to lose too much water. So then they close their stomata. As the stem replenishes that water, they open up again, and then they exceed their supply again, and then they close up again, like that. Not something that we would generally associate with health. Generally you would assume that the plant is going to sort of dose its or pace itself to not exceed its supply, but it's something that's actually quite beneficial if you live in a partially forested environment and you get high doses of light for brief periods of time during the day. So one of the other consequences of having low conductance is that you can't cool yourself, right? So like imagine a person who could not sweat being in a hot environment, right? You have no ability to cool your body, and so your body begins to overheat. So it's the same thing that's going on with citrus, that you see that red line is a fully sun-exposed leaf on a day where the air temperature is about 30, that says 35 degrees Fahrenheit. That's definitely not it. It's 35 degrees Celsius is the air temperature, and the leaf reaches about 45 degrees Celsius, about 10 degrees Celsius higher than the air temperature. Sorry about these timed slides. But what you also see is that a leaf that's under a 50% shade is much cooler. So the lack of conductance leads to really high leaf temperatures under warm conditions, and light seems to exacerbate that. So you see that slow water loss, which is actually the only way for plants to photosynthesize, is to open their stomata to be able to lose water and obtain carbon dioxide. So these two are closely linked. You can't have photosynthesis without losing water. But it also leads to high leaf temperature. So it directly suppresses photosynthesis, also leads to really high leaf temperatures that would be lethal to many, many plant species. So what happens when those leaves heat up? Is the citrus okay? On the right-hand side, you see these are thermal thresholds. So what we see is that citrus can tolerate easily 44 to 45 degrees Celsius in non-acclimated trees, and sort of a higher threshold. These are critical temperatures for when photochemistry begins to be lost, or the top part is when photochemistry is at like 50% loss. So that's a more severe threshold. But it can go up to 50 degrees Celsius and still retain a significant amount of photochemistry. So really resilient to high temperatures, right? The problem is that if you put the tree through a heating process, it's resilient, so it's not dying, but it loses productivity pretty massively. And I won't go into too much details, but what happened here was that the plants went through a period of gradual heating from 26 degrees as a high to 36 degrees as a high. This is a very normal weather pattern for Florida. This is not extreme temperatures. We're not talking about extreme scenarios. This is just normal weather. And then back down to 26 degrees. And what we saw was that at 33 degrees, they actually increased their photosynthetic capacity, but just at 3 degrees more heating, you see a massive loss in maximum photosynthesis. And not only does it go down when it's warm, but it stays down when it cools back down. And so the way that it does that is by protecting itself, right? So there's a trade-off between the mechanisms that lead to the resilience and the mechanisms that lead to photosynthesis. Won't get into too much detail, but I always like to bring up the example of Back to the Future. Has everybody seen Back to the Future? Probably some people are like too young for that. Yeah, okay. So when that scene where you know that lightning is going to strike and you know that either something really cool is going to happen, right? Time travel, or something terrible is going to happen and Doc is going to get fried again. That's what photosynthesis is like. That's what photosynthesis is like. When light strikes the leaf, either something amazing is going to happen, like photosynthesis, or something horrible is going to happen and that leaf is going to get fried because you have a massive amount of energy incident on the leaf and it has to do something with it. So if it can't put it into photosynthesis, then it has to put it into these protective processes. And that's what this yield of non-photochemical quenching is those protective processes. So what we see is that the plant kind of switches over into defensive mode and it's not able to photosynthesize anymore, which means that we have a really hardy plant. It's not going to die when the heat wave comes, but what is going to happen is it's not going to grow. So not only does this slow loss of water slow down carbon fixation, but it also leads to high leaf temperatures, which additionally suppresses the capacity for photosynthesis. And remember that I showed that that leaf heating occurs specifically in the context of high incident radiation. It doesn't heat up if there's not energy there to heat it up. So for a long time, I told people, well, citrus are shade plants, and that's that. And then a student of mine started to do some light curves, some photosynthetic light curves. This is carbon fixation at different incident radiations at the leaf level versus at the shoot level. And it turns out if you look at the shoot level, actually, well, first of all, I'll talk about the leaf level. At the leaf level, photosynthesis saturates at about 700 micromoles per meter squared per second. So that's about 1/3 of midday sun in Florida. Or midday sun in Belgium, for that matter, in the summer. However, when you incorporate the geometric complexity of a stem or of a shoot, actually the saturation point is closer to like 1800, which is much closer to full sun. And so it's not that it can't use the light, because actually leaves are not, perpendicular to the sun. So the context in which we measure that leaf scale is actually a little bit unrealistic. It's the shoot scale that's actually more realistic. it's not that it can't handle the light and put it into photosynthesis. What it can't do is keep up the water demand that's imposed on it by the light for an extended period of time. So it's that inability to maintain transpiration that leads it to not be well adapted to high light conditions. And remember, it won't show signs of stress. You don't. That's why in Florida you don't see plants looking sad unless they have a disease. But the plants looked happy until Huang Wenbing showed up. So then, what happens in the case of Huang Wenbing? What happens is phloem function is disrupted. I won't spend much time on this slide, but the basic idea is that the phloem translocation speed actually is slow to begin with. So most angiosperms have been measured at between 20 centimeters per hour and 100 centimeters per hour as their linear stem translocation rate. And citrus measurements are around here. We've taken other measurements in more realistic conditions and gotten, up in this range between 10 and 15, but still well below the typical angiosperm translocation speed. What happens in the case of Huang Wenbing is that translocation speed is reduced. You can see that in that rootstock X639, where you see, it goes from like 5 to less than 2 centimeters per hour, and then that feeds back into a reduction in carbon export from the leaf. Then what happens in terms of photosynthesis is that over time, those leaves, because they can't export more photosynthates, they actually, the new leaves that are produced are smaller and fewer. So it's not actually so much an issue of photosynthetic efficiency per surface area. It's just a reduction of total photosynthetic area that causes a decrease in growth. And that's kind of the explanation behind that loss of canopy density that you saw between the healthy trees and the diseased trees, where you see much fewer leaves. They are more yellow, but in fact, the yellowing doesn't reflect a reduction in carbon fixation. But the loss of leaves reflects a massive loss of potential growth. So you have this feedback process where the natural physiological process is that light is absorbed by pigments, which feeds into electron transport, which feeds into carbon fixation, which feeds into carbon export. And HLB blocks this carbon transport, which leads to feedback inhibition of carbon fixation, and it's kind of a logjam of energy at the electron transport and absorption levels. Okay, so now we have kind of a model of we have phloem translocation moving in both directions, xylem translocation moving primarily upward, with demands for water in opposing directions, light incident from above, water coming from below. So what happens in the case of HLB is you have fewer leaves at the top, they're less functional, you have greater penetration of light, and it exacerbates that cycle of low transpiration. You have a constriction of root growth because of the phloem dysfunction, and you get less water coming into the plant. The plant can no longer supply its leaves as effectively, and you have this vicious cycle of low photosynthesis, low transpiration, low growth, low supply of carbohydrates to the roots, as well as to the fruits, etc. So what are the things that we can do about that? Well, we can make irrigation and fertilization more efficient, right? So that fewer roots can still supply better nutrition and water status. We can work on phenology and morphology, and we can also impact the light environment. These are all things that are approaches that are available to growers. Other labs are working on irrigation and fertilization, so I won't talk about it, but it is important, and it's been shown that proper management strategies, or more efficient management strategies, can have really positive effects on tree growth of infected trees. I forgot to mention that after the rapid spread of Huanglong being through the state of Florida, and once the tree destruction practices were abandoned, we achieved pretty much endemic status, and we have about 99% infection rate. So every adult citrus tree, mature citrus tree in Florida, for all intents and purposes, is infected with this disease. So at this point, all management of citrus in Florida is management of diseased trees. If there are a few that have escaped, we're very happy about it, but they're not many. Okay, so the main points is we have slow water movement, high temperature reduces growth, slow carbon transport, which leads to slow photosynthesis. High light exacerbates both the photosynthetic and the hydrological characteristics, and HLB exacerbates all of those. So what can we do? A lot of people observed that we had feral citrus trees. The term feral refers to a domestic species that lives in the wild, right? So citrus is an introduced species, but because it's been introduced for a couple of hundred years, it grows in the natural forest environment in Florida. Growers started to point trees out that were in forested areas, and they said, well, why do those trees look so nice if nobody's irrigating or fertilizing or spraying insecticides or anything like that? So we took a natural area and we did a survey of about 60 trees. This is adjacent to a production area with highly symptomatic trees that were fertilized, irrigated, and had some management. What we found was that despite the fact that we looked over the course of about 3 months and through different methods of observation, we didn't find any of the vector. And that's quite unusual. I can go into any field and find the vector at just about any time of year, except maybe after a recent freeze. Only 3 out of 60 trees were found to be infected. And remember, half a mile from there, we're talking about a 99% infection rate in cultivated citrus. We also found no HLB symptoms in any of the trees that we surveyed, and we tried to find trees. We weren't. It wasn't even a random sample. We tried to find trees with symptoms. And another thing that we found was that the more intense the overstory shade in this natural area, the better the photochemical response is. And of the 3 trees that we found that were infected, we didn't observe any differences in the photochemical characteristics or starch or chlorophyll content. So just a little clue from that, not particularly applied, but that overstory shading reduces psyllid pressure and possibly disease. This is probably because of signaling. There's optical signaling to the insects, so they perceive the trees visually, and if they don't see them, then they can't find them. Right? So that's probably why we have such a low infection rate in the shaded area. So obviously, growing citrus in the forest itself is probably not a viable option for our currently 350,000 acres of citrus. But we thought, well, maybe we can use shade structures. So this is kind of a pilot study where we impose different intensities of shade, going from, of course, no shade at all the way to about 70% shade, which is pretty extreme. And what we found in the first 2 years was a really significant increase of yield in the moderately shaded treatments. And that actually continued, the trend continues for 2021. Apologize, it's of its own free will. So in general, what we see is that 30% shade shows pretty significant increase in yield over full sun. Increasing levels of shade after that actually go to decreasing yields. And so on the one hand, what we have is really like a scale of ideal to, or less ideal to more physiologically ideal conditions. So biologically, these are the healthiest trees, 70%, 50 to 70%. However, they're not very reproductive. So the example I always give to growers is that we have this stereotype of the young individual who still lives with their parents and plays video games in the basement all day long. That person is not very stressed, but their likelihood of reproduction is also very low. So that's kind of what's going on with this citrus. This is the one in the parent's basement. This one is out working but not making any money. And this one right here is kind of that happy medium. We see that reflected in growth too, where you see higher growth in all of the shade treatments, but especially in the 30% shade. This is the results of some metabolomic work done by some biochemists that we collaborate with. Starch is one of the main symptoms that we look at to look at severity of disease, because it's reflective of the total carbohydrate accumulation that the plant cannot export. So HLB infected trees have a hyper accumulation of starch in the leaves. And so what we see is that you see much more moderate levels of starch in the shaded leaves. Those are still more than what you would have if those trees were not diseased. But remember, we don't have that kind of a control to work with in the field in Florida. And one of the things that we notice is also within the carbon metabolic, well, the few metabolites that we're detecting here, everything is either unaffected or increased by shade, and only pseudoheptulose, which is also associated with zinc limitations, is associated with high light. So starch was negatively associated with sucrose, fructose, glucose, and pseudoheptulose 7P, which is an intermediate, but pseudoheptulose was positively correlated with starch. And then you see a similar correlation in the opposite direction with photochemistry. So photochemical measures that we did, which is the yield of photosystem 2 and the light or electron transport rate, which are actually both related to each other anyway, were positively correlated with especially sucrose and glucose, and negatively correlated or moderately negatively correlated with pseudoheptulose. So is it viable? It's viable biologically, but is it viable economically? Because none of this matters if growers won't do it. So here's an example of a place where it is viable. So in South Africa, they use these structures and actually in the absence of fungal bean disease. The primary issue for growers is cost. Structures are expensive to produce, especially compared to not building anything. And in Florida in particular, most of the citrus is low, it's sort of a low input citrus, so it's used for processing, so it's not for fresh consumption. You're not getting Florida mandarins in your grocery store, but you might be buying Florida orange juice. And so because of that, really it's only going to be viable for citrus that's for fresh production. The cost is, at this point at least, is too great for it to be viable for orange juice. There are other aspects that we don't know enough about. We don't know where, in terms of intensity and distribution of light, is that balance between stress, growth, and yield. We don't know about shade implementation measures, and we're still actually, we have some data, but I haven't gotten around to analyzing it about the impacts on psyllid, so vector arrival under these shaded conditions. So the main points are that we have an improvement in growth and yield in infected trees, and an improvement in health, especially in the 30 to 50% range. But there are some social and economic challenges to actually implementing that. So another way you can approach this is you can build your shade structure, or you can spray your shade onto the tree. There's a strategy called particle films. Particle films are sort of what they sound like. They are particles, they're actually colloids, usually clay, that are put in suspension in water, and they're sprayed on the leaves of plants. And then when that dries, they form a film over the surface of the plant. These are two examples from some of our experiments. This is a white one, that's one that's been dyed red. And what they do is that they reduce the intensity of light on the exterior of the canopy. That re-reflection actually helps distribute some of the light deeper into the canopy, so it gives a more balanced distribution of light. And because it changes what the plants look like, it can deter insect pests, preventing identification by the pest. So when my program started, there had been some preliminary work by entomologists that showed that that a white particle film, which is like a standard market product, was effective in deterring Asian citrusilla, more effective than most insecticides. Sorry. I did not, I'm spoiling everything. But they also found that if you dyed that particle film red with a red dye, which actually made it pink, it enhanced the deterrence of the arrival of bacilli. The explanation that they've given to me is that, well, red is a part of the spectrum that bacilli can't really perceive, and the white reflects a lot of UV radiation, which bacilli can perceive. So our work has what our work has done is taken that and looked at it in the field. We looked at transmission and disease transmission and growth. This is actually what was being done later. This isn't a mature planting. This is one of my students applying the treatment. You can see behind him on the right-hand side, that's the red treatment that's already been applied, and he's applying the white. In an actual production setting, you wouldn't use a sprayer like this. You'd use an air blast sprayer that would just go down and spray the whole thing at once. But since we're using small plots, we have to use this type of hand application. So what happened? We planted trees, uninfected trees, and then we monitored them for Asian citrusilla over time. We kept them applied with either red kaolin or white kaolin. We had an untreated control, so no insecticides. We had a foliar insecticide treatment, so it's like a grower standard, so what growers would typically do. And over time, what we found is that these two treatments, the red and the white, dramatically reduced the arrival of Asian citrusilla. Interestingly enough, the foliar insecticide resulted in more psyllid. It looks like it doesn't make sense, but it does make sense. I'll show you this in a second. And there was statistical differences between the white and the red, but the magnitude of those differences is not nearly as great as between kaolin and no kaolin. So over time, these treatments also affected the infection rate. So this is the proportion of trees in the field that are infected at various time points. So of course they all start off uninfected, and by the time we get to our first sampling, we already have like 15% infection rate after 6 months. I was really shocked that you could even detect it that quickly, but it was what it was. Interestingly enough, in the red kaolin, we didn't get a single positive detection until like a year and a quarter after planting. And by the first detection in the red treatment, the two controls were already above 50% infected. However, we did still reach 100% infection rate in all of the treatments by the end of 2.5 years. So it slows the transmission, but it doesn't come anywhere close to stopping it. But it also has really dramatic effects on growth. So this is not very good picture of cloud point data. So the company came and did some LiDAR scans of all of our trees in the field. And these are the median tree in each treatment. So you already know what that means. Half the trees in each treatment are smaller or larger than what you're seeing. And so the reason that we saw more psyllids in the foliar insecticide than the no insecticide is that the protection provided by the foliar insecticide led to more growth. And so there are larger trees that are more attractive to the psyllids later on. So that's why you did see that increase. But the most important thing here is that massive differences between kaolin treated trees and untreated trees. That's reflected in yield. The highest average yields were in red kaolin, but they weren't different from the white. And these are from the first well, the second year of growth through the fourth year of growth, but these are not economic yields by any means. This is just the beginning of an economic yield in year 4. But just to show what kinds of differences we're talking about in early yields. These 2 treatments are not on a good trajectory to ever becoming a viable, economically viable field, whereas these 2, we wouldn't call these high yields, but they're definitely on the way to actually being something that a grower would want. Okay, so main points are that the particle films delay infection by repelling agents such as psyllid. They enhance photosynthesis and show you data about water use, but they reduce water use, and that's one of the ways that they enhance growth, is that they reduce that over-transpiration. And red dye films, depending on which characteristic you look at, are either superior to or equal to the white, which was actually surprising to me. We have a study just ending in California, where they're very concerned about the arrival of HLB, which is more recent for them. And we see similar results with psyllids. We don't have a lot of growth data from them. So to sort of sum up all that I've talked about above ground canopy level manipulation, is that the ecophysiological characteristics of citrus reflect an adaptation to a partially shaded environment that reflects their origin as a gap species, and we can manipulate light intensity and distribution to both improve physiological performance and mitigate disease symptoms, and that can also have an impact on mitigating the transmission of the particular disease that we're talking about. It wouldn't necessarily have the same effect on other diseases. So what we're hoping to look at is get a better understanding of shade structures, how we can reduce costs, and how we can most effectively implement them. Particle films are low cost and the most compatible with what growers already do. They already have sprayers. They just have to put the stuff in the sprayer and spray it on. It's more expensive than some pesticides, but you don't have to do as many applications a year. So that's something that growers are beginning to adopt a lot, and every once in a while you see a pink field in Florida. And the other thing that we're looking into is intercropping. Can we grow other cash crop species that would be complementary and produce a more resilient system? You could, depending on the species and the site that you are using, get high returns from that. And it might be more resilient in terms of you have a more diversified landscape, and so you have less sharing of diseases and less susceptibility to the same factors, whether they be weather or biotic stresses. However, it requires a pretty significant change in production practices, and growers are not always really excited about this, completely redoing their way of doing things. Surprisingly enough, no one in the United States would believe that progress would come out of Alabama, but for the past 30 years, growers in Alabama have grown Satsuma mandarins under the shade of either pine trees or pecan trees. And they started doing that actually for frost protection from occasional frosts. It seems to work okay. They may not have the same economic constraints as growers in Florida do, but at least it's viable enough that they can keep it going. So we're just getting started on research there. And with that, I'd like to thank you very much for your attention, and I'd like to hear any questions. Yeah.
Yeah, very nice talk. I was wondering, we didn't talk about it. Is there resistance against this in Asia?
No. So there's no within the cultivated species, there's no resistance to the bacterium, and there's not really any resistance to the the psyllid either. There is tolerance to the disease to some degree. It's not evenly distributed, and there are probably different mechanisms of tolerance. And so a few varieties have been identified that are significantly more tolerant, but still affected by the disease. There's lots and lots of breeding work being done on trying to select that. It's a long process. Of course, you have a slow-growing tree and a slow-moving disease. So phenotyping is not fast. It's not something it's not like Arabidopsis and some foliar disease that you could do assays every 4 or 5 weeks or something. It's every 4 to 10 years is the cycle. But yes, what's that? In wild species, there's a fair amount of tolerance, and in one compatible wild species, there is resistance to the disease. And so there's been work to introgress those characteristics. There is actually, Poncirus is a related species, not part of the citrus genus, that's used as a rootstock. And actually, a breeder with the USDA developed the first edible Poncirus plant, but it's still not something like commercial yet. So people can plant it, but it doesn't yield enough to that growers would plant this on a large scale at this point. So there's progress in that direction, but it's just takes a long time.
So thank you, Christopher, for this very nice presentation. Very beautiful. About the shadowing system that you described, I was wondering what about when there are strong winds or a hurricane, and what is the duration on average of this? I guess it is nylon or plastic or something like that.
Yeah, so it depends a lot on the specifics of the material and the design of the structure. Right now, some high value citrus is grown in a protective screening system where they actually depend on absolute exclusion of the Asian citrus psyllid. So it's small screens, and what that does is it actually it's very effective as long as a hurricane doesn't blow your screen open. But because the strategy relies on absolute exclusion, the weakness is that if it fails at any point, then the disease is in. And so I know a few growers who have this system, 20 or 40 acres under this screen system. And when there are gaps, so for instance, when Hurricane Irma hit in 2017, it blew open, about 10 acres of one guy's production system. And we're talking about massive areas, so you don't just go out and fix that the next day. It takes maybe months to fix. And so in the meantime, of course, the disease occurred into his planting, and so now he's got about like 50% infection. So there is that weakness. However, if you're talking about relying on shade to mitigate current circumstances, it's not quite as big a deal if you lose your shade some period of time, because you're not talking about relying on absolute exclusion. You're just trying to, you kind of like with COVID, you're just trying to flatten the curve, right? You're not trying to completely eliminate it. So some structural designs can mitigate the likelihood of wind damage, but nothing is 100% sure in a place that's prone to windstorms. Where I grew up actually is also very wind prone, and my master's degree was on some production systems called high tunnels. So there's like low tech greenhouses that are covered in plastic. So it's very similar. You basically have a giant kite sitting out there, and so if any high winds come along, they will carry away your kite. And a lot of growers in the area where I was then were trying to build structures that would like withstand, bunkers basically to keep away the force of the winds. And I kept telling people the only way to keep a kite down in a windstorm is to collapse it, right? So you just have to not have the kite there. So what we're hoping to do is develop easily collapsible screens so that they can be you know, the nice thing, unlike where I grew up, the nice thing is that with hurricanes, you have warning, right? So you know 3 or 4 days in advance whether the hurricane's really going to hit you or not. So that's time to go out and do some stuff. Where I grew up, it was like you got 15 minutes, you know, because it's tornadoes, right? But with hurricanes, we have lots of time, and so, you know, people spend days boarding up their houses and stuff. You can do the same thing with a structure if you're willing to make that kind of investment. But still, we're talking about something that's not really viable for a low value production. It has to be a high value cultivar to make it worth it.